When we're trying to determine the amount of energy change in a reaction, sometimes a larger complex reaction can be actually made of smaller individual reactions, which we represent as a simplified larger reaction. One very simple example of this is photosynthesis. When we talk about photosynthesis, we make it look very simple, but in fact, it's a combination of hundreds of different smaller reactions, which we summarize and simplify as a very simple appearing reaction, even though we all know photosynthesis is not a simple reaction. Well, the way we could do this on paper is something called Hess's law. Hess's law basically is, or also known as Hess's law of heat summation, basically states that the overall change of energy, the overall change in energy, sorry, my pen's not working very well today, is equal to the sum, and of course, whenever you see the word sum, that means add, of all individual reactions. Okay, so again, if we have a larger, more complex reaction, which is actually a simplified version of smaller individual reactions, if we add up all the changes of the energy of those individual smaller reactions, according to Hess's law, that number to the overall change of energy. So the idea doesn't sound too groundbreaking, but when we try to do this in practice, you'll see this is not quite as easy as it may sound. So what we're going to do here in this very first example is it says, determine the change in enthalpy for the following reaction. So we want our reaction to be 2S plus 3 oxygens yields 2 sulfur trioxides. And what we don't know is what is the overall change of that top reaction. What we are given is the changes of reaction of the bottom. So what we're going to do is kind of work this like a puzzle, and we're going to try to figure out if we can move things around, switch things, flip things in order to get everything to cancel out of the bottom two reactions to match exactly the top reaction. Now, if that doesn't make sense, well, I'll show you what I'm talking about. So what I want you guys to notice is we have the S and the O2 there, S and O2 here. So what we're going to do is leave this first reaction here. We're going to leave this one alone. We're not going to flip it. We're not going to do anything with it yet. If you look at the second row, what you guys are going to notice is, or the second reaction, is that this one here doesn't quite look right. It needs to be on the right side of the arrow, not the left. And then this also corresponds with that. So notice how these are reversed. So what we need to do in this particular case is we need to take this second reaction on the bottom and we're going to reverse it. So I'm going to write this on the left side. So 2SO2 plus O2 yields what's on the left side, 2SO3. Now to do that, because we literally just flipped the reaction backwards, is I need to reverse the sign. Notice it was positive 198. Now it needs to be 198. Whenever we switch and flip the reaction around, we need to flip the sign on the delta H. So this, again, you can't ignore. What we have now is this one here, and we have this one here. If we could kind of combine them into one, then we might be able to get this one here, which again is what our goal is try to get that top one, the very top of this particular question. So let's see, we have the SO3 looks good, the 2SO3, so this match, that's good. We have 2SO2, okay, so I see a problem. Notice we have 2 on this side, but on the right side of the arrow, we only have 1. We need these to cancel out. So what I'm going to have to do is multiply all of this row by 2. So that's going to be 2S, 2O2, 2 that. So guess what? We multiply this by 2. That by 2 gives me, I'm going to have to calculate that real quick. If we multiply everything by 2 in the reaction, double everything, we have to double the enthalpy. So negative 297 times 2 gives me negative 594 kilojoules. Okay, so this again is no longer valid. So we've doubled that one. The one right below it, we have flipped the other direction. And so we flip from positive to negative. So now that we have that, I'm going to go ahead and combine this one and this one into one reaction. So I have 2S, I have 2 oxygens, that's that. Plus I have another oxygen there. So let me go ahead and make that 3 oxygens. Okay, then let's see. What I notice again is the SO2. This is going to cancel with this. Those are now gone. So we have, so far we have, let's see, and then moving on to the right side. Again, that's gone. We cancel because I keep looking at that one. Sorry, guys, that is gone. I cannot look at that. So on the right side of the arrow, this is gone. What we do have is this. Let me change that to an arrow. So what we have on the right side is only going to be 2SO3. So what I want to point out to you guys real quick is the fact that this and this now look the same, right? They're the exact same reaction. And the way we did that, of course, is we had to double, I'm going to call this reaction 1, and we had to flip reaction 2, which became this. I crossed off the 2SO2 because, again, one's on the left side, one's on the right side. These here did not cancel out. In fact, this and this come to give me this. Okay, hope you're following my logic here. And on the right side, all we have is this. There's nothing else there because that got crossed over, so that gets carried down. All right, now that we have been able to play with those reactions, flip them, double them, whatever we needed to do, what we need to do now is the math. So the way this works is we're going to add, because remember it says it is the sum of the two. So our delta H is going to equal our negative 594 kilojoules plus a negative 198 kilojoules. And what we get in the answer is, let's see, negative 594 plus negative 198, we get negative 792 kilojoules. Now, the only way to get that answer was for us to manipulate the equations above. Again, we had to kind of work like a puzzle. Again, reaction 1, we had to double in order to get 2S2 and 2 oxygens to go with the oxygen on the second equation, which of course we had to flip in order to get everything on the right side. We canceled out what was on both sides. The 2SO2 was on both sides. We canceled that out like you do normally in math, leaving everything behind, which gave us the starting equation at the top. Again, when we doubled our reaction 1, we doubled our enthalpy. When we flipped reaction 2, the sign on reaction 2. So let's go ahead and try some more because I know, again, your brains are probably hurting right now. So this example here, we have our starting reaction, which is this. We want everything to look, we want these 3 reactions here to look like the top one. So I'm going to go ahead and just simplify this and call this 1, 2, and 3. Remember, Hess's rule says that those 3 added together, the sum of those 3, those energies shown at the right, is going to equal the energy from that top reaction alone. So what we're going to do here is we're going to look at what we have. Notice what I'm noticing first is the C2H4, C2H4. So I don't think I need to do anything to reaction 1. Reaction 1 looks pretty good to me already. What I'm noticing here is on reaction 2, C2H6 is on the right side, but over here it's on the left side. So that's going to be a problem. So what I'm going to go ahead and do is I'm going to flip reaction 2, get the C2H6 on the right side. So I'm going to write the products as the reactants, 2CO2 plus 3H2O yields. Again, this is now gone. yields the original reactants, C2H6 plus 3.5 oxygens. This is now gone. And of course, it was a negative 1560. Again, now that becomes a positive 1560. So now I have my C2H6 on the right, my C2H6 on the right. Those are going to match. They look pretty good. Okay, on the bottom reaction, notice I have H2 on the left and H2 on the left. That looks pretty good. Okay, so let's see if this was good enough. So I'm going to go ahead and combine all three reactions into one big reaction. So here we go, all of this. C2H4, I have those 3 oxygens, and I have that half oxygen. So added together, I have 3.5 oxygens. Okay, so I got this, I got that, I got that. Also on the left, I have an H2. So that's gone. I have that. I have 2 CO2s, and I have 3 waters. Okay, so that's gone, that's gone. Now on the right side of the arrow, going one, I have CO2. Okay, I also have these 2 waters and that water, so that gives me 3 waters. Okay, and then that's gone and that's gone. And I got the CO2 already. There's 2 of those. Oops. And then I also have my C2H6. That's gone, and my 3 and oxygens. Okay, so what I just did there is I combined reactions 1, 2, and 3 into one massive reaction. All we need to do now is cancel out everything that is on both sides. For example, 3.5 oxygens, I meant to do that in red. Let's try it again. 3.5 oxygens cancels out with 3.5 oxygens. I have my 2 CO2 right there, 2 CO2 on this side. I have 3 waters on this side, 3 waters on that side. So what do I have left over? I have C2H4, which is this. I have plus 1H2, which is that. Nothing else on the left side. So now on the right side, nothing, nothing, only C2H6, which is that. Notice this looks exactly like that. So that is fortunate. So now we got our reaction correct. Everything's on the right side. All we had to do was flip reaction 2. So I'm going to go sum, add them all together. So negative 1411 point plus a positive 1560 plus negative 285.8, and my total is negative 136.8 kilojoules. There's our answer. That is the total amount of change of energy, which is the sum of those 3 other reactions, which again can be simplified by the reaction in black and also at the very top of the screen. All right, so that one went a little bit smoother. I like that one. The next one, unfortunately, I think is a little bit harder. So let's go ahead and jump into it. The next reaction we have is number 2. So for this one, what we're going to do is basically the exact same process. We're going to look at this reaction here and see if we could get reactions 1, 2, and 3 to cancel out to basically be the reaction at the very top of your screen. So again, looking at reaction 1, what I notice is I have a NO here and so what that tells me is I do not need to flip reaction 1. So that's good. When I look at reaction 2, I see N2H2 NH3. NH3 is on the left, NH3 is on the right side of the arrow. So what that tells me is we need to flip reaction number 2. Let's go ahead and do that now. So I'm going to put the products 2NH3 arrow, then my reactants N2 plus 3H2. This is now gone. We have flipped it, so I'm going to cross that out so I don't even look at it. And then I'm going to flip the sign. So this is now a positive 91.8. If it was positive, it would become negative. You just make it the opposite. So now my reaction 2 is in the correct configuration. 3, let's see, what about this one? Here we have an oxygen, and we have an oxygen. We have a water, and we have a water. So clearly that is also in the correct configuration. The right is right, and the left is left. Okay, what we need to do now is let's see if we need to multiply anything in order to make it work. For the NH3, notice I have 4. Here, I only have 2. So what we're probably going to need to do here is multiply reaction 2 by 2. So instead of being 2, that will become 4. And this will become 2 because it was a 1. And this 3 will, of course, become a 6. Now, when I did that, I also need to multiply this by 2 because I multiplied everything else in the reaction by 2. Okay, back to reaction 1. What I'm noticing here, again, 2NO needs to be 4NO. So let's go ahead and try multiplying reaction number 1 by 2. So that's going to be 2N2, 2O2, and 4O, meaning I need to double that one as well. Okay, looking at reaction 3. For this one, we have 2H2. I'm looking at my original equation, my O2. All right, so what I notice here is I already have 2 O2s and I have 1. I need 5. So that's a clue that I'm going to have to multiply reaction 3, but by what? My waters, this one's going to tell me because I need 6 and I currently only have 2. So clearly I'm going to have to multiply this one by 3. So instead of 2H2, that's going to be 6H2. This will be, instead of 1, it'll be 3. And instead of 2, this will be 6 as well. Multiplying everything by 3. So I need to multiply this by 3. All right, now I'm going to go ahead and combine all of this into one massive equation. So starting with reaction 1, I have N2 plus, 2N2, sorry, 2O2. Then I'm going on to my second reaction, plus N2. Okay, that actually, I'm going to go ahead and combine those. That'll make that 3. All right, then I have this, I have this, I have this. 3A, that gives me this. I'm going to go ahead and add 4NH. Oh, sorry, dang it. I just messed up. Let me go back. I was looking at the wrong thing, guys. I was messing up because what I didn't do is I didn't scratch this out. So I messed myself up. Okay, so I still got the 2N2. I still have the 2O2, so that's still correct. On the left side, I do not have this. Sorry, guys. I hope you caught my mistake. 4NH3, that's this. Nothing else on the left side. Moving to reaction 3, I have 6H2, and those 3 O2s will go with these 2 O2s, giving me 5 O2s. Okay, so I have that. I have that. So my left sides are completely done. So let me turn this into an arrow. Now I'm on the right side, reaction 1, I have 4NO. On reaction 2, I have 2N2 plus 6H2. And then on the reaction 3, I have 6 waters. Okay, so let's go ahead and see if anything cancels out. So what I see is this is going to cancel with this, so that's gone. I have 6 hydrogens, that's gone. That does not cancel. This does not cancel. That does not cancel, nor does that. So that leaves us a final reaction of 5O2 plus 4NH3 yields 4 NOs plus 6 waters. And again, that should look like that. Now, again, obviously my reactants are flipped, but that makes no difference. But my products are the same. Therefore, we have done it correctly. What we had to do was multiply reaction 1 by 2. We had to multiply reaction 2 by 2 and flip it. And reaction 3, we had to multiply by 3. So let's go ahead and figure out what all this equals. So negative 180.5 times 2 equals negative 361. The next one, Positive 91.8 times 2 equals, yes, I could do this a little easier on a calculator with using parentheses, which is what I would normally do, but I am trying to show you the thought process behind it. That's why I'm doing this the long way. That would equal negative 1450. Again, Hess's law is the sum of all of them added together. So negative 361 plus positive 183.6 plus negative 1450.8. My total answer is negative 1628.2 kilojoules. There is our final answer. That's the amount of energy that is represented by this very simplistic looking reaction once you understand that it's actually, that is the reaction in its entirety, made of those three smaller reactions above it. So that again is what's called Hess's law. All right, for the sake of time, and the bell's about to ring, I might put number 3 on another video. So stay tuned. Hold that thought, guys.